To open the first simulation, I'd like you to go to PHET Colorado and then scroll down to Physics. Then choose Motion from the menu. Then we're going to look for two different simulations. The first is the one shown previously in the video links. I'm going to open that just now. And the second is called Gravity and Orbits. To launch the first simulation, just click the play button on the projectile motion icon. We want to use the lab option, that's the one with the most options and detail. And then you can see various things here. The first is the zoom in and zoom out. That's quite self-explanatory. There are a pair of measuring tools in this little bubble that we don't really need. There is a description of the values that you've chosen. There are a whole range of options associated with things like the gravity or air resistance, the object's shape and mass and so on. It turns out none of this apart from the gravitational field strength makes any difference at all as long as we're ignoring air resistance, which is what we're going to do. Down at the bottom we can see our cannon that can be raised up and down, its angle can be changed, and the slider controls the initial speed of the projectile. The red button shoots, and the yellow button erases the previous reading. The first experiment I would like you to do is to investigate the impact of changing the initial speed on the trajectory of the projectile. The trajectory is just a fancy word for path, really. So looking here, we've got our starting height at 0, the starting angle at 80, that matches the instructions, and we're going to set a speed of about 4 and hit the fire button. We can see that the simulation shows the path is still inside the cannon, which isn't very realistic. If you have a more decent speed though, you'll notice that the path gets further and further away from the cannon and becomes quite realistic and useful. You may need to zoom out if you have a very big range. What I'd then like you to do is take a screenshot. There is a guide on this link here. It involves pressing the control button and then the Windows button on your Chromebook. You have two options. Control plus the show windows allows you to take a shot of the whole screen and you'll have to then trim it down, or Control Shift Windows allows you to then choose which part of your screen you want to take a picture of. My one's set up to be similar as that. It might look something like this. You drag over what it is you want to capture. Notice I'm including the bits at the bottom for a little context, and then in your Google Doc you need to paste it in. If I try and do that with the keys, it gives you a reminder of the shortcut, which is Control plus V. You might find that you need to resize it in order to get it to fit with the text, and sometimes it can be a little bit awkward. Control Z for undo is a very useful way to correct any mistakes that it might decide to make. Now we have our image into a Google Doc, we might need to modify it a little bit in order to make it work nicely with the rest of the things there. The three little icons at the bottom are probably the most important. They control how the image lines itself up against other text. My favourite is the wrap text option in the middle. This means that you can move it around freely and the text will automatically go around the object. I also like to tell it to lock the position in place with fixed position. That way if I later move something around, I don't have to worry about the images jumping about on the page. Personally, I much prefer to just have to manually correct things myself rather than letting the software get a little bit carried away doing whatever it thinks I want it to do. Usually computers are not very good at guessing what we really want. If you want to label the different trajectories, well, it's a bit tricky in Google Docs, but you can take the image, put it into slides, add some labels on, and then take it back into the Google Doc. It is a bit tricky though. The Microsoft package works a bit easier, and I can show you the result that I made in the past to give you an indication what the ideal practice would be here. For now though, it's not super important, we're just doing this as a learning exercise. Do note that the simulation only keeps up to 5 different trajectories. So if you have loads and loads and loads of them, well, that might be great and all, but you might find that you've actually deleted your earlier ones. For the second experiment, we're going to clear the previous work by hitting the restart button, and then what we're going to do is have a look at different launch angles. The lowest angle when the cannon's on the ground here is 25 degrees, so that's a good place to start, and we're going to fire. And then we'll carefully adjust it to be about 15 degrees bigger, and then again, and then again. The nice thing about the simulation is it still plays while you make other adjustments. If you don't have a mouse, this might be a bit trickier. It's not super important that you get exactly the same angles. Okay, as long as they're reasonably spread out, this will work just fine. I'm going to take a screenshot of this one here showing a wide range of angles, paste that into my Google Doc, leave that for later, and then what I want to do is have a little bit more of a look at the sort of optimal range. You see, this very big angle, that clearly doesn't get us very far. The very small angle, well, it's okay, but this sort of range about here seems to be the most important thing. So I'm going to restart, and then I'm going to focus round about the 45 degree angle. 45 degrees, most people usually know, is about the optimum. That's technically true only if there's no friction, but for most purposes on Earth, that really is the case. So I have up to 5 trajectories I can show at once, so I'm going to choose one of them at 45, 2 below and 2 above. So going in units of about 5, I'll launch one at 35, then I'm going to choose to do the higher one, just so those are the faded out ones at the end, and then I'll choose 40, 50, and then 45 exactly in the middle. The interesting thing you might note here is that all of these trajectories are actually quite similar, even though we have a difference of up to 20 degrees, which is huge, by the way. Most of these projectiles are landing really within maybe a meter or two of each other. This is one of the nice things about the 45 degree launch angle, one of the nice things the way physics works. Not only is it the best angle to throw out if you're wanting lots of range, it's also quite forgiving. You get a bit of wiggle room. The third experiment involves investigating the role of the starting height. You see, you don't always just throw things from ground level. Perhaps you're standing on top of a mountain or a hill or a rooftop, that sort of thing. Most people know that if you're shooting things off of a wall or a cliff or a harbour wall, it's going to help you throw things a bit further. And really, there isn't much more to learn than that. But we'll generate some data just to see. It doesn't take long. The maximum is 15 in this software, and we again have 5 different options, so I'm going up every 3 meters. And again, we'll take a screenshot, add it to our work. Actually, it's in the wrong place. Add it to our work. And then comments. For the gravity and orbit simulation, we want to choose the model version. This gets rid of the pesky problem of reality, which is the spaces are huge and the objects are tiny compared to that, which means it doesn't really work. So in the model version, we get around that problem. We can see here we have different options. The one it starts with is the Earth-Sun system, but I want you to go with the Earth-Moon system here, and turn on velocity, turn on the path, and turn on the grid. You can turn on the gravity force arrows if you prefer, but they get in the way sometimes. We have the zoom bar over here, and this fast and slow motion sometimes can be useful. So what we want to do is change the height of our moon that it starts at. Imagine that you're launching something from a very big hill or something like Newton's thought experiment, and we want to see what effect that has. So I'm starting here at 1 box of orbit height, and according to my instructions, my velocity vector will be 1 box in the right direction. So I hit play, and oh no, I've destroyed the moon. No worries, we'll get it back in a moment. But what I want to do is take a screenshot. So I'm pushing my screenshot button. Yours is slightly different. And then you could try and paste it in here, but actually we're going to have several, so it's going to need a bit of editing. So what I'd like you to do is paste it into Google Slides. We'll come back to that in a moment. Shrink it down a little too. So back to my simulation. I'm going to hit pause, because if I don't hit pause, if I reset, it just crashes straight away. So I'm going to hit pause, then reset, and now I get to change the position of my moon. I'm going to go up to 1.5 boxes. I hit play, and this time it's slightly different, although similar. I'll take another screenshot, add it to Google Slides, and try the next value. And oh look, we have a nice lovely orbit. Go back into Slides, hitting paste again, that gives me the third image. Now you could try this for a whole range of them. I'm not going to spoil the whole process for you. Now you might ask, why have I put them into Slides? Well, I'm going to show you a little rather simple, quite universal picture editing technique that allows you to get around the fact that sometimes the software has its own preferences and it sort of gets in the way of what you want to do. I want to label these things, so I'm going to add a text box and I want to type in some names. So this one was a crash, and I'm going to say the starting height was equal to 1 box. If you make your window bigger, you'll see that there's actually a few other tools available here. For example, I might center align my label here, and I might sort of line up in the middle of the image. Control C to copy that text box, Control V to paste it, and I'll just save myself some time by making labels for the others here all at once. The second crash, well, it wasn't really the same as the first. I'm going to say this was on the far side. It's sort of like we crashed almost behind where you could see. It went round the Earth a bit and then it crashed. And that was for a starting height of 1.5 boxes. And the second one, well, this was an orbit. You might say it's an elliptical orbit. And that happened when we had 2 boxes of height. So I've generated my 3 images with their captions on Google Slides, and now I'm going to take another screenshot of the whole lot together. And this is the clever bit. When I do that, I can now insert it into Google Docs without having to worry about it doing anything to my labels. Normally if you try and do this, they'll all get jumbled, they'll get resized, and it can become a bit of a pain. By creating an image, it's all stuck as one thing, and by creating an image, it makes it far harder for the programs to ruin them or modify them or cause weird and wonderful behavior. I would do it normally for more than 3 examples, but that'll do for now to show you. We would write in each of these boxes what the behavior is, and that would complete that task. Going down to the second of the experiments within this package, what we want to do is now change the speed that we're starting at. So the instructions say place the moon 1 box away, and this time we're going to shoot off to the left. The reason for that is we stay away from this menu, gives us a bit more space. So first speed is 1, and we see it crashes just like last time. But then if you increase the speed to 1.25 boxes, you might get something else. Again, maybe take some screenshots as you go, but you can always add them in later if you prefer to do it that way. So now I'm going to take it to 1.5 boxes, and well, we're still crashing, but it's getting slightly better. At 2 boxes, we have an orbit. So what we've now actually seen is you can make an orbit in one of two ways. In this second example, what we needed to do was increase the speed to match the height we were starting at. Whereas in the first one, what we did was we matched the height to the speed that we had. The overall message here is that for any particular orbit, there is a correct speed to be in to achieve that height. If you get the balance a bit off, you end up with an elliptical orbit. If you're very far off, well, you'll either crash or your object will escape altogether. Let's see if we can now do that. So if I increase this to 3, maybe I should zoom out. What you'll see is that our moon has just went off. It's gone. That means that the speed was too high to maintain the orbit. If you're just a little bit short of that escape speed, what you can end up with is quite a highly elliptical orbit. Pluto is a bit like this when it orbits around the Earth. And there's even speculation that there might be a 9th planet out there that does this as well, that we haven't yet found. Many meteors have these type orbits too. So like before, I would take my multiple screenshots, I would add some labels, and then I would combine them all together to make my little report. I'm not going to show you all of that just now, but here's a sneak peek at what the answers might look like. Our third task is to try and use this software to investigate meteors. Now you see, if you have motion where you're at 90 degrees to the sort of line between where you are and the object, that makes a line. And if you're moving at 90 degrees to that, that's a sort of orbital type motion or trajectory. What we're going to do is we're going to start off a decent distance away with a path that doesn't really lend itself well to orbits. So 2 down here, and then we're going to go 1, 2, 3, 4, 5, 6 away. I've experimented with. And then instead of having a velocity vector that's sort of 90 degrees to the radius line like this one, that would be very good for making an orbit, we're going to instead treat this as if it was a meteor. Something that might be heading in a funny type direction compared to other orbits. So if we start off with our speed in this direction, well, that's not going to lend itself towards an orbit. Instead, what you'll notice, you either get the meteor's path being redirected, or, well, you get a collision, which is obviously not very good for the people on the planet. So at a speed vector of 1 box, the object crashes. If we're slightly higher, we might just be able to have a near miss. See that there's a near miss, and the trajectory of the meteor has been substantially changed. I would describe this as a sort of slingshot maneuver, which is often used in space flight trajectories, trying to change the direction of a space probe without burning too much fuel. It's quite clever. If you have a bit less, if you have a very, very small speed, well, then you're definitely going to be captured by Earth. Oof, bad news indeed. If you have a very big speed, well, then you're not. You're going to be able to escape. You're going to just keep going. Depending on the actual speed, depends on how big an angle that you deflect by. You might also experiment with things like this mass of the Earth or the mass of our moon. So if you have a more massive object, for example, well, then it's a bit better at capturing things. The sort of minimum speed that it needs to get by will be a bit less. Just like before, take some screenshots as you go along, add some labels, and then fill in the table on your Google Doc describing the behavior, and add us a few comments. If you really want to go a bit further with this, you can follow this link here at the end. This isn't the higher material, this requires knowledge of an advanced equation for central force, but that's actually the key link